Hi class. So what we're going to talk about now is polarity. So what we want to be able to do is take a molecule and look at it and decide how polar it's going to be. And not necessarily in terms of calculating an actual numerical value, but just trying to look at it and say, is this a polar, non-polar molecule? If we have a couple of molecules, being able to look at them and compare which one would be the most polar. Alright, so the first thing we want to do is kind of look at the individual bonds, alright, and see when we look at all the bonds, is there a general direction to the polarity? Alright, this first one, carbon and hydrogen have very similar electronegativity values. So if you remember, electronegativity is one of those periodic table trends we're going to memorize. And if we start at the bottom and go across, with fluorine being the most electronegative, and hydrogen's the weird one where it kind of sits here next to carbon instead of being over here where it usually is. Alright, so carbon and hydrogen actually have a very similar electronegativity value. And so since there's not really a dipole moment between any of these bonds, we're going to say it's nonpolar. Even if these atoms have been very polar, if they're all the exact same spreading out, they essentially cancel each other out. Right, so if we look at this molecule, we're going to say it's nonpolar. Alright, and I'm going to go a little bit out of order, but if we look at the one just below it, each one of these bonds is very polar, right? Fluorine's very electronegative, so it's going to pull the electrons towards the fluorine. Alright, so on each one of these, we're going to pull the electronegativity away from the carbon. But if you notice, they're all pulling out, right? We're pulling all away from the carbon. So even though each one of these bonds is very polar, overall, they're actually going to cancel each other out. So net, the molecule itself, is also nonpolar. And so in actuality, if we had an atom or a molecule that looked like this, where only two of them were fluorines, and maybe the other ones were hydrogens, even though we have two less polar atoms, since we would have some kind of net dipole in this direction, this would actually be more polar than the one with four fluorines. And it's because we have a general directionality to it, right? There's a direction towards the polarity of the bonds. If they're all going in opposite directions, they actually cancel each other out. Right, so that's kind of the problem with this one. All right, let's look at water. So water is one of the more polar molecules we'll see. And same idea, oxygen's much more electronegative than the hydrogen. So all the electron density is being pulled towards the oxygen. So then we have this greater net dipole moment going up in this case, the way the molecule is drawn. So this would be a very polar molecule. All right, so water is a really good example of a polar molecule. Same idea if we look at the one just below it, if we look at carbon dioxide. Same as the idea behind this trifluoride one. All right, so we have this carbon tetrafluoride. There's four fluorines that are all canceling each other out. Same idea here. The carbon-oxygen bonds are very polar. Right? The oxygen is much more electronegative. It's a double bond, so it really amplifies this effect. So the electrons are really pulling out away from the carbon. Right? We're pulling them away from the carbon. But since these are 180 degrees, so exactly opposite each other, they actually cancel each other out. Right? It's similar to if we had a tug of war. If the two people are equal strength, they'll cancel each other out, and that's what happens here. So this actually becomes a nonpolar molecule. Now, on the other hand, if we have something like a ketone, right? So down here we have our ketone, we have just one carbonyl going up, right? And then we have our carbons here, and so they have the same electronegativity value, so there's really no dipole moment there. So the only dipole moment we have is going up, right, from this oxygen-carbon double bond. And since we have a general direction to it, this is going to be a polar molecule. All right, so that's why this is polar. Even though the bonds on the carbon dioxide, each one is very polar, this one has a direction to it. So that's why we have a dipole moment, and it's a polar molecule. All right, the next one, same idea. Do you notice how the two fluorines, right, are on the same side? So overall, we have a dipole moment going this direction. All right, so this would be polar. If, for example, we had something that looked like this. All right, where the two fluorines are exactly opposite each other, this would be much less polar, right? Even though it has the same very polar bonds. Right? This bond's really polar, and this bond's really polar, but they're essentially going opposite each other, so they cancel each other out. All right, same idea. If we took something like this, and we put the fluorines on the same side off the same carbon, this would be polar. All right, because now we still have these dipole moments towards the fluorine, but now we have a general idea of where the dipole moment is going in one direction. All right, so this is how we can kind of look at, is a molecule polar or not? So we want to look at each of the individual bonds and then see, do they have a general directionality to them? Are they all kind of pulling in the same direction, or are they canceling each other out? All right, let's look at one more. Same idea here. Each one of these chlorines is much more electronegative than the boron, so we're going to have a dipole moment out towards them. But now if you notice, same as one of the previous examples, they're all pulling out, right? They're all spreading out, so they're going to cancel each other out, so this is going to be nonpolar. Now, if we do something where we put a boron, and then there's a fluorine on one, and then hydrogens on the other side, now we've kind of canceled that out because we do have a good dipole moment where it's just going up, and so this would be polar. Okay. So one of the things we have to be careful about is comparing the difference between a polar bond, right? Because these bonds are very polar, so we definitely have some polar bonds, but overall the molecule is nonpolar because they cancel each other out, right? So the polar bonds have to have some direction to them. All right, hopefully this helped.